What you see next will shock you. A Physics Final Project by Jenna Sigmund. Here, we have these two globes on sticks. Not those. Thank you. These two globes on sticks are called the Van de Graaff generator. A Van de Graaff generator is a device designed to create static electricity and make it available for experimentation. Our history of this machine begins here. In the early 1930s, American physicist Robert Jemison Van de Graaff invented the Van de Graaff generator in 1931 at Princeton. He went to this beautiful university known as Oxford to do some research. While at Oxford, Van de Graaff was impressed with the need for a source of energetic beams of subatomic particles for the study of atomic behavior. He created the idea for the Van de Graaff generator, and upon returning to the United States in 1929, continued to develop it. So, our experiment is, what would happen if we touched a Van de Graaff generator at 200,000 volts? Well, I'm glad you asked. Even if you didn't ask, we're going to find out. So we know that voltage is a measurement of energy over charge. In a flashlight, there are only 1.5 volts. How many volts are in a 9-volt battery? Obviously 9. What about in an outlet? You can easily touch the battery in a flashlight or the 9-volt battery, but we don't touch outlets. It's common sense. Why? Because we know we'll get electrocuted. An outlet gives off 120 volts, so it would be safe to assume that we shouldn't touch something that holds 200,000 volts. And we're done! Just kidding. You thought we were done. In this experiment, since we found that we can touch something at 200,000 volts, we'll be using Ohm's law, which is V equals I times R to find the current. V stands for voltage, I stands for current, R stands for resistance. We'll be using my good friend Sarah in this demonstration. If Sarah shakes her head around, her hair begins to float off her head. This is a pretty good thing considering you could get electrocuted at 120 volts. So that begs the question, why? Why is she not dead yet? Why is she not looking like this guy? Her body is storing the voltage. She's not getting electrocuted because if she stands on the ground, the only insulation she would get in her shoe, which usually isn't enough. We don't want the electrons to flow through her body and into the ground. The volts aren't moving around or going anywhere. That's why they're all trapped inside of her body. Since the person's hair follicles are getting charged up to the same potential, they try to repel each other. This is why the hair actually stands up. It would not make a difference if the polarity of the Van de Graaff generator were reversed. As long as the person is insulated, the charge will build up, assuming of course that the hair is clean and dry. In this experiment, since she actually can touch something at 200,000 volts, we know that the voltage is 200,000 volts. We have to find our current. We know the resistance is 40 million ohms when using an ohm meter. And so, our current is going to be 0.005 amps. A Van de Graaff generator creates static electricity. The current generated by a Van de Graaff generator remains the same, while the voltage changes according to the applied load. A very simple Van de Graaff generator is made of the following: a motor, 2 rollers, an insulated belt, 2 brushes, and a metasphere as the output terminal. The motor is required to turn the belt at a constant speed around the 2 rollers. When the motor starts turning the belt around the lower roller, electrons are captured from the insulated belt onto the lower roller. Slowly, more and more charge becomes concentrated on the roller. This phenomenon of concentration of charge results in the repelling the electrons from the tips of the brush assembly. It also starts to attract electrons from the air molecules between the lower roller and brush assembly. Due to this phenomenon, the positively charged air molecules get carried on the belt away from the negatively charged roller. The belt therefore gets charged positively and moves towards the upper rollers. The upper brush is directly connected to the inside of the output terminal, or sphere at one end, and almost touches the upper roller and belt at the other. The electrons in the brush become attracted to the positive charges on the belt. The air particles break down too, and the free electrons move towards the belt. The sphere takes up all of the charge, and the excess charge gets spread to the outside of the terminal output or sphere. That's why Sarah's hair was standing up. This device is used to produce a very high electrostatic potential, up to 20 million volts. When the motor is turned on, the lower roller charger begins turning the belt. Since the belt is made of rubber, and the lower roller is covered in silicone tape, the lower roller begins to build a negative charge, and the belt builds a positive charge. You can understand why this imbalance occurs by looking at the triboelectric series list. This list is a list of materials showing which have a greater tendency to become positive and which have a greater tendency to become negative. Silicon is more negative than rubber. Therefore, the lower roller is capturing electrons from the belt as it passes over the roller. Thank you! I hope you all learned something new.